So yesterday morning, we started to talk about vector spaces. So a vector space V is a set with two operations. I should say a vector space V over a field. By a field, we mean, I'll call it F for field, which is usually the real numbers or the complex numbers. So a vector space over, so you have two kinds of vector spaces. One where the scalars are real numbers, the other where the scalars are complex numbers. And almost everything we do will be true for either real or complex numbers. So because everyone is more familiar with the reals, I'm going to talk about real vector spaces, but you should know that every theorem is for real vector spaces is true as well for complex vector spaces. So a vector space V is a set with two operations. We can add vectors. We have vector addition, and we have scalar multiplication. And I've written down now a couple of times the properties that vector addition and scalar multiplication have to satisfy. So I don't need to do it again. And a subset W of V is a subspace, a vector subspace, if it satisfies the three conditions that the zero vector that's the vector that no matter what vector you add it to, it doesn't change the vector, just like the number zero. W is closed under vector addition. So if you take two vectors in W, the sum is in W, and W is also closed under scalar multiplication. And we have the fundamental operation of taking a linear combination of vectors. If V1 up to Vk are vectors, and C1 up to Ck are scalars, then C1 times V1 plus C2 times V2 and so forth up to CVK is a linear combination. Of the sequence of vectors V1 up to Vk. And we say that the sequence of vectors V1 up to Vk is linearly dependent if there is a sequence of scalars C1 up to Ck, not all zero. Some can be zero, but they can't all be zero, such that C1 V1 up to Ck Vk gives us the zero vector. So for example, in every vector space, the sequence of vectors V minus V is linearly dependent because 1 times V plus No, actually, I can say the sequence of vectors v comma v. These are the same vector, right? But it's a sequence. So v comma v plus minus 1 comma v is the 0 vector. And these scalars are not 0. So, in fact, also, if you take any vectors v, so for every sequence, let's just say v1, so every sequence, let's say the 0 vector, v1, v2, and v3, is also linearly dependent. Let me just put a little arrow over this just to emphasize that this is the 0 vector and not the number 0. This sequence of vectors is linearly dependent because, for example, 7 times the 0 vector plus 0 times v1 plus 0 times v2 plus 0 times v3 is still the 0 vector. We showed that the number 0 times any vector is the 0 vector, and any number times the 0 vector is the 0 vector. So you're just adding the 0 vector 4 times, and you get the 0 vector. So these are sequences which are linearly dependent. And a sequence of vectors v1 up to vk is linearly independent if it's not linearly dependent, or what is equivalent, if there is if whenever c1v1 plus c2v2 plus ckvk equals the 0 vector, whenever you have a linear combination of the vectors equals 0, then c1 is 0, c2 is 0, all the scalars are 0. That's what it means to be linearly independent. So, for example, we know that M sub nn of F, that's the set of all m by n matrices, is a vector space for any m and n. So, for example, if we're looking at 2 by 2 matrices, the matrix 1, 0, 0, 1, and the matrix 1, 1, 0, 1, these two matrices are linearly independent. Why? Because if the 0 matrix, that's the 0 in this vector space, is some linear combination of these two, when you add these two matrices together, you get C1 plus C2, C1, 0, C1 plus C2. So that means each of these coordinates is 0. So C1 is 0, and C1 plus C2 is 0, which means C2 is 0, which means these vectors are linearly independent. Right? So this is an example. So an important theorem that I proved on Wednesday morning says the following: let S be a subset, not a subspace, but a subset of a vector space V, let W be the set of all linear combinations of vectors in S. That means W is everything that every vector you can write is in the form C1S1 plus C2S2 up to C sub S, C sub K, S sub K, where S1 up to SK is just some finite sequence of vectors in S, and the C1 up to CK are scalars. They're in the field. And just to make things a little bit clearer, then make sure S is a non-empty subset. So there's something in S. So then W is a subspace of V. So if you take any non-empty subset of a vector space and you look at all linear combinations of the vectors in the subset, we claim that's a subspace. And the proof is pretty straightforward. First of all, if S is not empty, there exists some vector S1 in S, and so 0 times S1, that's a linear combination of just S1, and that's the 0 vector, so that's in W. So W contains 0. And if you have some linear combination, I can write it as summation C sub I, S sub I goes from 1 to K. That's just a linear combination of vectors in S. And another linear combination, say C sub J prime, S sub J prime, say J goes from 1 to L. But you don't have to have the same number of vectors in a linear combination. So this is some linear combination of K vectors in S, and this is a linear combination of L vectors in S. And if you add them, you get some sum you just get a big linear combination of these vectors plus these vectors. So this says the set W is closed under vector addition. And if you multiply this by a scalar, this distributes across, and you just get another linear combination. So W contains the 0 vector, is closed under vector addition, and is closed under scalar multiplication. Any questions about this? And there's a very nice way to characterize the subspace. So we say that W is the subspace generated by S. And if we let, I don't know, script S be the set of all subspaces of V that contain S, if you take the intersection of all of the subspaces in S, this means the set of all vectors that belong to every, let me call this W prime in S, that's equal to the subspace generated by S. Call it W sub S, just to emphasize that. So the subspace generated by S can also be described as the intersection of all the subspaces of the vector space that contain S. So that's just interesting kind of geometry, if you like. So we have two important notions. We have the idea of a set S of vectors generates a subspace. And we have the idea of linear dependence and independence. And these are connected in several important theorems. And here is one of the most important, which I proved yesterday, and I will prove again because it's so important. So the theorem says the following: let S be a set of m vectors contained in a vector space V, and let W be the subspace of V generated by W, and let V1 up to Vn be n vectors in W. So the theorem says if n is bigger than m, that is, if you have m generators for your subspace and you choose n different vectors in the subspace, then these n vectors must be linearly dependent. And the proof comes down to the theorem that we proved at the very beginning, which says that if you have a system of homogeneous equations with more variables than equations, then there's always a non-zero solution. Okay, so how does the proof go? I have n vectors. So for every j from 1 up to n, the vector vj is in the subspace generated by S. That means the set of all linear combinations of vectors in S. So Vj is some sum Aij S sub I. I goes from 1 to m, where the Aij's are scalars, real numbers. Right? Every one of these vectors Vj is a linear combination of the S's. And so the question is, can you find the linear combination of the Vj's equal to 0, the 0 vector, with not all of the scalars 0? So we want to sort of solve the vector equation x1 v1 plus x2 v2 up to xn vn equal to the 0 vector. What are all possible linear combinations? If the only possible linear combination is with the x's all 0, then these are linearly independent. But if their x is not all 0 that solve this equation, then the vectors are linearly dependent. So we have the 0 vector is summation. Let me just use sigma notation because it's easier. Summation j goes from 1 to n, x sub j vj. That's this linear combination. This is summation j goes from 1 to n, x sub j. But vj has this representation as a linear combination. Summation I goes from 1 up to m, aij s sub I. So I can bring this inside here. This is summation j goes from 1 to n, summation I goes from 1 to m, aij xj si. And when you have finite summations, you can interchange the order of summation. This is summation I goes from 1 up to m, summation j goes from 1 up to n, aij xj times si. That's this scalar, this is just a number, times si. And we want to know if that's the 0 vector. Now, it would certainly be the 0 vector if all of these numbers, summation aij xj, is 0. So we can ask, do there exist scalars x1 up to x sub n, not all 0, such that this was our equation in vectors. This is always 0. Summation j goes from 1 to n, aij xj equals 0. For all I from 1 up to m. But you look at this, this is just a series of linear equations that are homogeneous. Right? When I equals 1, this is the equation a11x1, a12x2, up to a1n equals 0. When I is 2, this is the equation, well, this equation, all the way down to the last equation when I is equal to m, am1x1 plus am2x2 plus amn(xn) equals 0. So this is a system of m homogeneous equations in n variables with n bigger than m. That was our hypothesis. There are m vectors in the set S and n vectors in the subspace generated by S and n bigger than m. But by our theorem on homogeneous equations, there exists a solution which is not all zeros, not the 0 vector. Well, this is from the theorem on linear systems of homogeneous equations. So you can have x is not all 0, such that this is the 0 vector, which means v1 up to vn are linearly dependent. So this is linearly dependent. And the sort of equivalent statement of this, the contrapositive, is that S be a set of M vectors and let W, I'll just write it like this, be the subspace of V generated by S, if V1 up to Vn are vectors in W that are linearly independent, then N is at most M. Because if you had more than M vectors in W, they would be linearly dependent. So every linearly independent set has at most M vectors in it. So this is basically a review of what I did yesterday, and let's move forward. So we can state the following theorem. Let S be a non-empty set of vectors in a vector space V and let W be the subspace generated by S. So let me insert a definition. A basis for a vector space or for a subspace of the vector space is a set B contained in the subspace with the following two properties. B generates W. So every vector in W is a linear combination of the vectors in the basis. And second, B is a linearly independent set of vectors. So this is a basis. We know that if you take any set S, all of its linear combinations form a subspace. And a basis for a subspace is a set of vectors that generates the subspace and is also linearly independent. And my theorem that I'm in the process of stating says, if you take any non-empty set of vectors in V and you let W be the subspace it generates, there exists a linearly independent subset of S that also generates W. In other words, if you have a set S that generates a subspace, and we're making it slightly easier, finite, then it contains a basis.
Also, if it is linearly independent and is a linear combinations of all the vectors, then that means it's a basis, right?
Correct. So if your set, if you a basis of a subspace or of a vector space is a set which generates the space, that means that every vector is a linear combination of the vectors in V, and the set is linearly independent. I should say also, S is not just zero. So, because if you take the zero vector, the subspace it generates is just zero. So S is a non-empty finite set of vectors, and it's not just the zero set. That's the right. So suppose we let S be W1 up to WK. These are the vectors in S, non-zero vectors. So all of these vectors is non-zero. So the idea of the proof is the following. I mean, there are two cases. If S is linearly independent, you're done. So suppose the set S is linearly dependent. So that means you can write the zero vector as some linear combination of your vectors with at least one of the scalars non-zero. Say C sub I1. Maybe just to make it clear, I'll just say C1. So you have if these vectors are linearly dependent, some linear combination of the vectors is zero, and some coordinate C1 up to CK, at least one of them is non-zero. So suppose C1 is non-zero. So then you can just write the following: C1W1 or minus C1W1 is C2WK up to C sub KWK. I just brought this to the other side. And because C1 is non-zero, I can divide by it. So W1 is C2 over minus C1 times W2 up to CK over minus C1 WK. In other words, if this coefficient C1 is not zero, then W1 is in fact a linear combination of the vectors W2 up to WK. But what that tells me is the following. we know that every vector in W is some linear combination. I'll call it A1 W1 plus A2 W2 up to A sub k WK. Remember, S is the set of k vectors, and we just proved that W1 is some linear combination of W2 up to WK. So I can take this formula for W1 and plug it in here. So W, which is a linear combination of W1 up to WK, can be written as A1 times, let me just write this in sigma notation so it's easier. This is minus C sub I over C1 W sub I, sorry, summation I goes from 2 up to K minus CI over C1. So I have A1, or I just write it in, it's like times W1, which is minus C2 over C1 W2, minus C3 over C1 W3, up to minus CK over C1 WK, plus A2 W2 plus A3 W3 plus A sub K WK. So my vector W, when I collect the coefficients of W2, W3, and so forth, this is a linear combination of W2 up to WK. I don't really need W1. So W, which is the subspace generated by this set S with K vectors in it, if these vectors are linearly dependent, I get the same subspace by, let's say, S1, where I throw out the vector W1. This is just W2 up to WK. So W is the subspace generated by S. If S is linearly dependent, I can throw away one of the vectors. I get a smaller set S. It has one fewer vector, but it still generates W. And I can iterate or repeat this argument. If this set is linearly dependent, then I can throw away some vector and I get a smaller set which generates the same subspace. And if that set is linearly dependent, I can keep throwing away vectors. But this is a finite set. I can't throw away everything, because if I threw away everything, the subspace generated by the empty set, we call that 0, but it certainly doesn't contain a non-zero vector. So at some point, this process has to stop. So let's say we iterate this, I might call it deletion process. We keep deleting one vector after another, and then this algorithm stops, and we obtain a subset, let's say S prime of S, that generates the same subspace W and is linearly independent. And that's the proof. That's this beautiful proof of the result that says if you have a finite set S that generates a subspace, it always contains a subset that is linearly independent and contains the same subspace and generates the same subspace. In other words, every finite generating set contains a basis. And this now enables us to do something very important. We can define the dimension of a vector space. So the number of elements in a set is called the cardinality of the set. And the cardinality or size of a set S is denoted by S with absolute value signs around it. So for example, if S is the set 2, 4, and 17, the cardinality of S is 3 because there are 3 elements in this set. So here is our theorem. It says, let W be a finitely generated subspace of a vector space V. That B1 and B2 bases for the subspace. Remember, a basis for a subspace is a set of vectors that generates the subspace and is linearly independent. And the theorem says that the number of elements in the first basis must be equal to the number of elements in the second basis. If you have a finitely generated subspace, the number of elements is the same in each of them. And the proof is very pretty. It says the following. Suppose that B1 contains M elements. And B2 contains N elements. So B1 generates the subspace. B2 is contained in the subspace. And a theorem said that if you have a subspace generated by M vectors, and if you take N vectors in the subspace, if the N vectors are linearly independent, then N is at most M. Because B2 is a linearly independent set. Right? Remember, a basis has 2 properties. It generates and it's linearly independent. So let's look at those 2 properties separately. The set B1 generates, it has M vectors. The set B2 is independent, it has N vectors. So N is less than or equal to M. Okay. And now let's also look at it in the opposite way. The set B2 generates W. The set B1 is contained in W. And the vectors in B1 are linearly independent. So I have M vectors linearly independent in a space generated by N vectors. So M is less than or equal to N. Because the set B1 is linearly independent. And from these 2 inequalities, N less than or equal to M, M less than or equal to N, M equals N. That's what we had to prove. M equals N.
I have a question, Professor. So, how do we know like one vector generates a subset? Like you know, like how you said B1 generate W.
Correct.
Like how do we know that?
No, it's not. This is, it's like saying, you know, take the number 3. And you say, well, how do we know it's the number 3? And I say, it's because I said, take the number 3. That's the number I want to take.
Oh, okay, okay.
Right? So here I say we have a subspace of a vector space W, and we're given 2 different bases for W. So W has, the subspace has 2 different bases, and one of them has M elements and the other has N elements. And we just proved that M must equal N. They have to have the same number of elements. So it's not a question is why is B1 a basis? What I'm saying is let B1 be any basis and let B2 be any other basis. And if you do that, then we prove they have the same number of elements.
Oh, okay. I just one more thing. Let's say like we wanted to prove that that a vector that one vector as a subspace of W, let's say, is a basis. So there's 2 things that we need to check, right?
Well,
The linear.
wait, you have to be a little bit careful. When you say one vector is a basis, that means you have a base. So your vector space is just all the scalar multiples of one particular vector. So that's okay, but that's a very special case of a subspace.
Right, but like okay, let's say like let's say that we wanted to prove that like B1 right, like the B1 like forms a basis for W, right? So to prove that, we needed to check if the linear combination of B is linearly independent. And if it was linearly independent, it forms a basis, because that's what the proof you just did said, right?
Well,
But like,
the definition of a basis is a basis for a subspace is a set of vectors that has 2 properties. It generates the subspace. So every vector in the subspace is a linear combination of vectors in the basis. And the set of vectors in the basis is linearly independent. So that's the definition of a basis.
oh, all right. And if it wasn't linearly independent, then
It's not a basis.
then it's not a basis. But like you just said, if it is a finite generating set, then it contains a basis, right?
Correct.
Oh, okay.
Yeah. And so now we can define the dimension of a vector space is the number of elements in a basis. And we just proved that's well defined. Now, let's look at a simple example. Suppose we take R2, which is all the vectors x, y. And I've been saying this is 2-dimensional. And here's a proof. So take the vector E1 to be 1, 0, and E2 to be 0, 1. So my set B consists of these 2 different vectors. And if I take any vector x, y, I can write that as x0 plus 0, y, which is x times 1, 0 plus y times 0, 1, which is x times the vector e1 plus y times the vector e2. So every vector in R2 is a linear combination of e1 and e2. So the set B, this set, generates R2. But I also claim these vectors are linearly independent. So suppose 0, that is the 0 vector, is some linear combination of e1 and e2. But that's this, which when I add is xy, which means x equal y equals 0. So that means the only linear combination of e1 and e2 that produces the 0 vector is 0, 0. So the set B is linearly independent. So therefore, the set B is a basis. And the dimension of R2, DIM stands for dimension, is the cardinality of B, and B has 2 vectors in it. It's 2. So with my definition of the dimension of a vector space, I just proved that R2 is 2-dimensional. So that's pretty good. And by exactly the same reasoning, you can prove that the dimension of R3 is 3, and in general, the dimension of Rn is n. In the case of R3, we take the vectors 1, 0, 0. For example, you can take other sets, 0, 1, 0, and 0, 0, 1, and any vector x1, x2, x3 is x1, e1 plus x2, e2 plus x3, e3. So this formula tells you on the one hand that every vector is a linear combination of e1, e2, and e3. So the set of e1, e2, e3 generates R3. And conversely, if some linear combination is the 0 vector, then x1, x2, and x3 would have to be 0. So that proves that these 3 vectors are linearly independent. And they form a basis. In general, for Rn, you take the vectors, well, you take the vector e sub I, which has all 0 coordinates, except a 1 in the ith space. The ith coordinate is 0, is 1, and all the other coordinates are 0. And the set consisting of e1, e2, up to en is a basis for Rn. Any vector x1 through xn is a linear combination x1, e1 plus x2, e2 up to xn, en. So this formula says 2 things. It says the vectors e1 up to en generate Rn because every vector is a linear combination of them. And the only linear combination that's 0 is the one in which all the x's are 0. So this really is a basis, and dimension of Rn is equal to Rn. If you took the vector space of 2 by 2 matrices, right? So this is all matrices A, B, C, D. This has as sort of an obvious basis the four matrices 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And every matrix is a linear combination of these. A, B, C, D is A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. So this formula expresses every matrix as a linear combination of these four. And conversely, by this formula, if a linear combination of these four matrices is the zero matrix, then A, B, C, and D have to be zero. So this is the basis, and the dimension of the vector space of 2 by 2 matrices is 4. So it's extremely important and useful in mathematics when you can assign a dimension to some object, and this now is a way to assign the dimension of a vector space. So that's pretty good for us. Okay. All right, well, it's getting interesting now. So that is the story for this morning. Are there any questions before I log off? Okay, then we are done for now. All right, bye.